if you think of adding a new point in the determinantal setting, because of repulsion, it will be repelled away from all the existing points and will be forced to find an equilibrium location, which is probably going to be in the middle of some less populated place in this square. And in terms of the question of fluctuations, which I alluded to earlier, so of course there is, in random matrix theory, there are these famous results. Ofer talked about it a little bit yesterday in his lecture. So in certain kinds of settings for nice smooth functions, if you are considering linear statistics, the asymptotic, and you start scaling them, the asymptotic variance is of order 1. Okay, it doesn't blow up. So that's some example of stability or suppressed fluctuation for determinantal processes. We'll have the occasion to come to it in more detail. But from this figure, you can also already see some element of that. So for example, if you are if you have a function on this domain and you are trying to, let's say, do quadrature for that function based on this point. So you do not want to calculate the full integral over everything. Instead, you want to, let's say, average or sum your function over your sample points, and you want to use that as a proxy for your integral. Then the point is that in that case, if you are using a uniform random sample, your samples or the information that you gain from about your function that you gain from your samples would be highly biased towards the clumps, and it will be not really informative about the vacant spaces. So if your function has some special behavior in this region, it will not be captured by the uniform random points. Whereas for determinantal, it's going to be already, because of the much spatially homogeneous spread, the quadrature using determinantal points will be much better, and one can prove some quantitative theorems to this to quantify and clarify this state. But anyway, so let us now introduce the first model that we are interested in today. So, of course, in a DPP, if you look back at the definition, so it's in a sense you can think of it. So in a DPP, classically there is a kernel and there is a background measure. But usually, and particularly, we will be interested in finite universal sets today. So usually, in under like broad circumstances, you can absorb the background measure into the kernel. So we will just focus on the kernel for today's talk. So a determinantal probability measure is actually parameterized by the kernel. So you can think of the kernel as a parameter, but as a parameter, it's a little bit too big. And as we saw in Machiy-Sovchnikov's theorem, it's just a positive contraction. That's all that it needs to be, and it's a big class of operators or big class of matrices, even on a finite universal set. So what is really of interest, and if your class of if your parameter space is too big and unwieldy, then of course it can cover a lot more examples, a lot more applications, but it's usually harder to work with, because in order to be very effective, you want to have a parameter that incorporates not that's the parameter space should not be very large. Okay. So what we are interested in is that we want let's say a subspace of these kernels, which has interesting features. It has interesting stochastic features. It captures various kinds of interesting settings on one hand, and yet it should it should be a small subspace or a small subset of this full parameter space of contraction operators. So that's our goal. And so this is what we would call a robust parametric model. And what we would additionally want is that if we vary the parameter k, the kernel k within this parameter space, then the impact on the statistical behavior of the points should be easily interpretable. And for example, we can compare. So for example, we can compare this question to the well-known exponential family models in probability. So for example, exponential random graph models in which is popular in stochastic networks. So these are precisely classes, explicit classes of probability distributions on graphs for which which are parameterized by a small number of parameters, and you can prove various detailed structural results because of that fact. So to this end, we propose the model of Gaussian determinantal process, which will be indexed by the space of positive definite matrices of a given dimension. And for lack of a good name, we just call this positive definite parameterizing matrix as scattering matrix. We'll come to the explicit formula for the kernel in one or two slides. But the idea is that we are looking for a determinantal process with a Gaussian kernel. Okay, and this in turn would be a testing ground to understand the response of the spatial behavior of the point process to parameter modulations in the space of scattering matrices. And we will unveil some connections to spiked models of random matrices and spiked PCA, and this is based on joint work with Philippe Rigoldin. So DPP is characterized by an underlying kernel, as we saw. So this is our parameter, and again, just to reiterate, what we are interested in is to reduce from this huge space of non-negative definite contraction kernels to manageable low-dimensional parameterized subspace of kernels, which is nonetheless still interesting. GDP is the abbreviation for Gaussian determinantal process. So the point it's going to be a translation invariant point process on the Euclidean space RD, and the kernel is simply the kernel kxy will be of the form x minus y. It will be a function of x minus y, and the kernel is going to be simply the d-dimensional Gaussian density with some positive definite covariance matrix, and this is what we are calling the scattering matrix, just to distinguish it from the the covariance or the correlations between the points. Okay, so there are two quantities here. So one is the correlation between the points in the physical space, and then there is this quantity sigma, which is the covariance matrix of the Gaussian, and we want to separate these two concepts very neatly, so we use the name scattering matrix for sigma. Okay, so sigma is our parameter, and for what values so what is the class of sigma for which this is a valid Gaussian density? It's it's the class of positive definite matrices of dimension d, and it can be shown basically using this theorem, the Machi-Soshnikov theorem, that for any such Gaussian density, and I should really write k sub sigma here, for any such Gaussian density with positive definite covariance matrix sigma, we have it satisfies the condition of the Machi-Soshnikov theorem, and we get a determinantal point process. And by construction, the kernel is a function of x minus y. So the points, it is a translation invariant point process living on the Euclidean space R to the d. So let us do some quick checks. So what is the mean density of points? So the average density of points is the probability at the point x, is the probability that x belongs to the DPP, or the probability density, and this is just, if you just blindly use the determinantal formula, it's just determinant kxx, and this is a single number, so it's really just kxx. And this kxx here is just a constant. This is natural because the point process is translation invariant. And it is up to a dimensionally dependent constant. It is just 1 over square root of the determinant. Okay. So this actually is going to be a useful fact when we later study parameter modulations for this model. And what is our observation? So what are the points that we observe? So generally speaking, of course, it's an infinite point set in the continuum. But in practice, and even for for simulation purposes, we are only going to be able to handle a finite number of points, and this finite number of points is usually going to be all the points of the Gaussian determinantal process that fall within a ball of radius r in dimension d. And our goal is to interpret what happens when we vary this parameter sigma in the space of positive definite matrices, and in particular, what is its impact on the behavior or the distribution of the points in the physical space. So what kind of so we are now dealing with the space of d cross d positive definite matrices. It's a much smaller space than the full space of general kernels, but still it is reasonably big. It's of the order d square dimensions. So we want to still further reduce to some specific kinds of modulations which are going to give which are going to have nice structural implications for the point process. So one thing is that if we modulate sigma such that the determinant of sigma changes, then the mean density also changes. So if I am allowed to look at these points, then I can just take the average number of points per unit area, and that's going to be an approximation to this mean density. And as soon as the mean density, as soon as sigma is perturbed to sigma tilde such that the mean density has changed, the determinant has changed, it is easily recognizable just by computing the average density. And generally, the average density has very good concentration properties if we average over a ball of large radius r. So modulating sigma such that determinant sigma changes will lead to change in mean density and can be detected simply by estimating the average density of the observed points. And therefore, we will focus on parametric modulation that leaves determinant sigma invariant. And it is similar to shear mappings or shear transformations. So, and as I alluded to, even within the space of positive definite matrices, we are going to focus on a key family of modulations, which will be in the form of spiked models in the space PD, which is PD is the space of d cross d matrices, positive definite matrices. So our perturbations or our parameter modulations will be of this form. So generally speaking, when we think of so let's say we start from the identity, and just to give you a heads up, the key impact of this kind of changes, this kind of parameter modulation, will be on the strength of the repulsion of the determinantal process, which will vary which will vary from one direction to another because of the introduction of the spike. So if we start from identity, which is the base case, which is the isotropic case. So there is no directional bias in the dependency structure. So the strength of the repulsion is equally strong in all directions when sigma is identity. And then usually one would say that, okay, maybe you introduce a spike, we need to be positive definite. So u is a unit vector. So you introduce a spike in the direction u, maybe with some strength alpha. Okay. So this is the sort of the usual notion of a spiked model. But the point is that we also want the determinant to stay fixed. So as a result, the right way to parameterize this is to actually introduce the spike in your chosen direction u, where u is a unit vector. And then, of course, if you do not do anything, if you take this matrix, this will change the determinant of sigma. So what you do is that you mitigate the effect of that change by distributing this effect uniformly in the orthogonal over the orthogonal directions to u. Okay, so that's why this is the structure. And this lambda equal to 0 is it is no spikes, which means that sigma is identity. So this is the isotropic model, and there is no directional bias in the dependency structure. And lambda bigger than 0 corresponds to a spiked model that introduces directional bias in the strength of the dependency structure. In particular, the repulsion between the points is much stronger. For example, much more long ranged on the scale of 1 plus lambda in the spike direction. So just for the sake of understanding, think of lambda as very, very large. So then if you move 2 points away from each other along the direction u, then really you have to travel, you will feel the repulsion between them on the scale when they are separated as far as 1 plus lambda. On the other hand, because of the adjustment in the orthogonal directions, the dependence in the directions orthogonal to the spike is much weaker and decouples to almost independent behavior at relatively short length scales. So let's try to. So now, if you have if you see a bunch of points, a bunch of random points within our observation window, which is a ball of radius r, and then we want to understand whether there is some dependency between these points. We want to understand whether this is this dependency is isotropic versus whether there is a directional bias in the structure, in the dependency structure of the points. So we can model this by a Gaussian determinantal process, and then we want to. So then within the spiked model of Gaussian determinantal processes, the question will be that whether sigma is identity, or some constant times identity, versus whether there is an actual spike which sort of dominates all the other directions. Okay, so that will be the simplest notion of there being a directional bias, there being a preferred direction of strong repulsion in this model. And for this, we can try to estimate sigma from these observed points, and this turns out to be a good estimator. So this small r is a threshold parameter, which is of the order which can be taken to be of the order square root d log n. So that's the optimal value. And what I would really ask you is to not care about these leading constants, which are like various kinds of normalizations, centering, and paraphernalia. And the real deal is this sum. This is the sum of rank 1 matrices. And it's a sum of rank 1 matrices, which is summed over pairs of points, but only neighboring pairs of points. Okay, and there is a lot of there is a fair amount of literature on sums of rank 1 random matrices. So these xi's and xj's are random points. So these are actually this is actually a sum of rank 1 random matrices. So there is a fair bit of literature on the sum of rank 1 random matrices. Except that usually they are taken to be independent. So in this case, they are really dependent random variables, and they depend on pairs of points. But still, the structure is simple enough. So we believe that using the explicit determinantal structure, one might be able to perform some explicit or detailed structural results about this kind of sum of independent random matrices. Or sum of dependent random matrices. And actually, to be honest, in the usual literature on sum of rank 1 random matrices, these matrices themselves are taken to be independent. So here in this particular structure, even if the points xi, so in this case, the points xi are coming from a DPP, but even if the points xi were actually independent, they were independently sampled from this domain, even then these are not independent rank 1 matrices because they involve both xi and xj. So there is going to be a certain kind of dependency between some of these rank 1 matrices. So even for independent random points, a sum of rank 1 matrices like this is I don't think there is the toolkit to study such rank 1 sums is fully developed yet, and that can be an interesting question in itself. Now that we have this now that we have this candidate matrix sigma hat, this estimator of sigma, we know that as the observation window, it goes to infinity, it converges to sigma. What we want to do is that we want to, on the basis of sigma hat, we want to, which we can compute just on the basis of the given points that are falling in the observation window, we want to decide whether there is a spike or whether sigma is actually identity. And so this, in terms of the spiked model, this is equivalent to testing for the presence of a spike. And what we can show is that by looking at how large the operator norm of sigma hat is. So sigma hat is a random matrix. So by looking at its operator norm, we can, and depending on how big it is, we can detect the spike with high probability if the spike size is above the threshold. So this is similar to the spike model recovery in random matrices. You can recover the spike only if it is bigger than a certain threshold. And the question is, what that threshold is or how low you can push that threshold. So here this threshold is of this form, and it looks a bit complicated because it is written in terms of D and R. But if you have an observation window of radius R in D dimensions, then the number of points N is roughly of the order R to the D. And if you use that, you can, for example, if you look at the denominator, it's R to the 1 over R to the D by 2, which is 1 over square root N. So if you kind of interpret this in terms of N, you will see many of the usual parameters in the rates of parametric statistical models starting to appear. So this is, it looks a little different because it is written in terms of D and R, but actually you can sort of uncover many of the usual suspects of parametric statistics within the ambit of this result. And once we have determined, and if we decide that if on the basis of this test we decide that there is a preferred direction in which the repulsion is stronger than the other, so it is not an isotropic model. So then the natural question is, what is this preferred direction in which isotropy is broken? And that can be understood or that can be estimated by looking at the leading eigenvector. And we also have quantitative guarantees on how good the approximation of the leading eigenvector is to the actual spike direction. Okay. So this can be applied to the question of dimension reduction, but in the interest of time, and probably this is not the most interesting topic for the present audience, we can, I'm skipping this, but just to mention that we can actually apply this as an answers to actual real world data, and you can, in our method, actually GDP based methods actually arguably they perform better than standard PCA based methods. Okay? And this is the clustering problem on some standard clustered data. Let me now, in the last 15 minutes or so, let me move to another realization of a determinantal process in a very different context, but again a new kind of determinantal process. And it will also lead to some new kinds of random matrices. So this is an application to stochastic gradient descent. So it is it is everywhere in these days. Any kind of optimization you want to do, people use stochastic gradient descent. So let me just quickly summarize what the key method is. So you have this function FL. So generally, this is the symbol L is being used because it's some kind of a loss function. So it depends on some data point observation and some parameter theta. So our goal is to find the optimal value of the parameter theta, and this is basically a landscape or the likelihood landscape of theta. For example, if L is the likelihood function, and we are trying to find the, for example, minimize the negative log likelihood, which is the maximal likelihood estimator, which is here. So basically, we want, and this is the basic step of gradient descent. So what you do is that you average your gradient. So you want to do gradient flow in the variable theta in this landscape. So this is a landscape which is parameterized by theta. So you want to do gradient flow there, which is just flowing along the slope in that landscape. But you do not know what the actual gradient is. So you estimate the actual gradient by averaging over the data points that you are given. And then this is changing the parameter. So if you are at theta t, you just flow along the gradient with step size eta t. Okay. And then you get to your next point in the iteration of gradient descent and you continue. So this is a very popular procedure in optimization. But the point is that recently we have a very large data set, which is a boon, but also a bane for this kind of procedure because your capital N will be super large. And if capital N is super large, you have to remember that you have to do this computation at every step of your gradient descent. So at every step, you have to do this order n computation, which is too expensive. So what people do instead is that they replace this average over the full data set by some kind of a functional. Also, it's also going to be some kind of a weighted average over a subset of the data set. So you draw a small subsample of your full data set, which we call A, and this L of A, comma theta t is just this L of A is just some kind of a weighted average of your function on just on this subsample. So instead of doing order n computations at every iteration, you do order the size of A computations. So this is a significant drop. And usually this subsample is taken to be quite small. So this reduces the computational load quite considerably. This kind of a subsample is called a minibatch. And as you can imagine, trying to draw the, sampling these sets, random subsets A, in a good way is going to be very important for how well our gradient descent process converges, or how good this approximation is. So generally speaking, what happens is that you draw a random subset, a subsample called a mini batch, which we denote by A, and then you take a weighted average of your function over that mini batch. So, for example, the natural problem is how to select the random subset A, and what is the nature of randomness that leads to improved performance of the SGT procedure. And just to tell you how this, how the behavior of the random subset A sort of ties in with the performance of the convergence guarantees for the gradient descent. So here is a famous result by Bach and Moulines from 2011, where they show that if sigma square is the variance of your gradient estimator, then essentially the leading order term here is the first term. So essentially the mean squared error actually scale, it can be upper bounded by sigma square. So basically, so here T is the number of steps you have already taken. So basically, if you can reduce the fluctuations of this, if you can choose A such that choose the subsample A, the mini batch A such that the fluctuations or the variance of this gradient estimator is suppressed, then you are going to do much better with respect to convergence of gradient descent. So the goal is to make sigma square small as a function of the batch size P. So P is the size of the mini batch A, and the default thing to do is to sample A is to draw the mini batch A uniformly at random, and then take the usual empirical average on A to construct the gradient estimator. And for this, the variance is known to be of the order 1 over the batch size. And our approach, what the alternative possibility is to select A according to a DPP, so as to suppress the variance sigma square. And this pertains to our earlier discussion on how the uniform spatial homogeneous distribution of DPP points actually reduces the fluctuations of linear statistics. And our DPP sampler will be tailored to the data distribution, and it will be implemented via orthogonal polynomials. So what is our procedure? So let me quickly sort of go over it. So imagine that for definiteless, let us imagine that our points are living on sort of a hypercube of in dimension D. And you can think of multivariate orthogonal polynomials living on this hypercube. So these are just obtained by doing Gram-Schmidt on the usual monomials with respect to the reference measure Q. So Q, for example, you can take Lebesgue measure or Jacobi measures, etc. And then so this is a sequence of orthogonal orthonormal polynomial functions phi k, which are multivariate. And then you can construct your DPP kernel by taking the projection onto the first P orthogonal polynomials. Okay, so this is the classic orthogonal polynomial ensemble of rank P with respect to the background measure Q. Okay, So far so good. This is, you know, classical. So these objects are known. So the point is that we can try to use a DPP kernel like this, except for two problems. The first problem is that this doesn't have anything to do with our given data points. And more importantly, if you sample from this kind of a DPP, you are going to just get some generic points in the continuum space -1, 1 to the D. You're not going to, whereas your mini batch has to be a subset of your given discrete data points. So what you do is that, so this is the multivariate orthogonal polynomial ensemble, and the number of sample points. But one good part is that because it is a projection kernel, the number of sample points is always equal to P, which is the rank of this projection. So let us try to sort of mitigate these other problems which I mentioned. The first thing to do is to use the, so suppose we are given a large number of data points, then using that we can form an approximation of the underlying distribution from the population distribution from which the data are coming. So we can use some kernel density estimator or something like that, and then we do the multivariate orthogonal polynomials, and we can get points, but they are in general not going to be related to the data set in any way. So what we do is that we take this original multivariate orthogonal polynomial of rank P, and we conjugate it by this factor. So here our approximation to the data distribution gamma tilde enters. So this now factors in the data. Okay, so the data has already, the distribution of the data has already entered into the picture, and these are projections on the. These are projections. So this kernel is also a projection on the same space, but with respect to a different background measure. So you can sample from this KQ gamma tilde and get P points, P random subset. But these points are still going to be some generic points in the continuum. They are not going to be a subset of your given data set. Okay, so to generate a subset that specifically lies within your given data set, what we do is that we do the naive thing, and we try to simply restrict this kernel to your data set. So D is a discrete set of discrete points. So D is your given data point. So let's say Z1, Z2, Zn, which lies in this hypercube. We want to sample a subset of D. So far, what we know is that, so D are some points here. So this is D. What we know is what we had is the ability to sample points from this sphere, from this continuum space, and then by restricting the kernel, we try to get something out of which is a subset of D. But the problem is that if you do this naive restriction, this is no longer a projection, and this is important for various reduction purposes, which is our main goal here, because if it is not a projection, then the variance tends to be higher. So what we do is that, but the given data points and gamma tilde, the empirical measure of the given data points D is an approximation to gamma tilde, right? Because there are a lot of data, and gamma tilde is basically close to the population data distribution. So gamma tilde and the empirical measure of the data points is quite close, and using that, we can argue that although KQ gamma tilde restricted to D is not on the nose projection, but it is still approximately a rank P projection because of the proximity between gamma tilde and the empirical measure of the data points. And we can use this observation to spectrally round off KQ gamma tilde to an actual rank P projection K tilde which lives on the data set. So now K tilde is actually a discrete kernel which lives on the data points, whose rows and columns are indexed by the data points, and is a rank P projection. And so this is our DPP, and we sample the mini batch A according to this DPP. And because the way things have been set up, we always get P points, which is the desired number of points. And our gradient estimator is a weighted average of the gradient of your true function, and the weights are inverses of. So this is not a simple average, right? So this is a weighted average, and the weights are given by the diagonal entries of k tilde in this manner. And then one can direct computation shows that it is actually unbiased, and some orthogonal polynomial analysis using the celebrated Christoffel-Darby formula tells you that actually the variance, there is an improvement in the exponent of the variance. So the variance, if you do uniform random sampling, it would be order 1 over p inverse. Here it's p to the minus 1 plus 1 over d. So there is an actual improvement in the exponent of convergence. And by Bach-Mullilen's theorem, this directly leads to an improvement in the exponent of convergence of the gradient descent algorithm. We are what is near completion is so one important observation here is that we are interested in the gradient estimator. So this is what we are interested in, right? And for that, this sigma A DPP is what we are interested in, and generating the subset A is a step on the way. So if someone could give us a direct way to sample from the, so this is like a vector valued random variable. So if someone could give us a direct way of generating samples from this sigma A DPP, we would not care anymore about the minibatch. Okay. So so using the fact that this is a so-called linear statistic of the DPP, if you think of it, this is a linear combination, linear combination of a function integrated against the sort of the empirical measure of the DPP. So this is a so-called linear statistic of the DPP, and it has a very nice structure. It'll take just 1 minute. So using that fact, so for example, the Laplace transform of sigma A DPP, this has explicit determinantal formulas. Using those, we have a method of completely bypassing the generation of the mini batch, which can still be a computationally expensive procedure, and using the Laplace transform and the explicit determinantal formula for the Laplace transform of this gradient estimator to directly generate samples from the sigma A DPP. So this is a work that is close to being completed. So hopefully we can submit within a month or two, and then then of course we get a much better computational savings and advantages. Okay, so there were some other things, but the time is up, and these are some references. And at the end of the reference list, you can see the well-known book of on zeros of Gaussian analytic functions and determinantal point processes, of which one of the authors is Manju, who is with us here today. So any questions about DPPs, please feel free to ask Manju. Thanks.
I guess everybody wants to have lunch, so we'll conclude the session and thank all speakers this morning. Thank you.